Okay, example 14. Remember that we're thinking about using Q versus K, or do we just plug in for K or plug in for Q? We got to have everything at equilibrium to be able to plug things in to an expression of K or Kp. So as I read this problem, I see that I have an equation that has all gases, so I know they're all going to be included in my calculations. It tells me the temperature. I don't care about temperature. It tells me what my K is. So equilibrium constant. So we know K to be 5.10. Okay. Last problem I went over, problem 13, we had to solve for K. This time they give us K. It says calculate the equilibrium concentration of all species if 1 mole of each component is mixed at 3 liters in a flask. Okay, in a 3-liter flask. Okay, so that means that if we're looking for the concentrations of equilibrium, we have initial concentrations. So we're going to figure out, we know that all of them, so all of these are going to have a concentration, right? So remember that's moles over liters of 1.000 moles over 3.00 liters. So we're going to do 1 divided by 3, which hopefully we don't have to do that on our calculators too terribly often. So we're going to get 3.33 times 10 to the negative first big M. Okay. And we know these are all I's. Remember, the next step was to say when I get a concentration or a pressure, is that concentration or pressure describing an initial position or an equilibrium position? Based on this word problem, we have to assume these are initial positions because it tells us to calculate equilibrium concentrations, and if that was done, we would be done. We just have to do this. If this was at equilibrium, we'd be done with the problem. Okay, so we know because we have initial concentrations, we need an ice chart. So we're going to do CO plus H2O going to CO2 plus H2. All of these can be included in my ice chart and do not have to be X'd out because all of these are gases. So we're thinking about ICE. We know that we have initial values for everything. So this is going to be 3.33 times 10 to the negative first. This is going to be 3.33 times 10 to the negative first, and 3.33 times 10 to the negative first, and as always, or I shouldn't say as always, I guess, but as consistent in this problem now. Okay, now we need to do the C part. That's the change. That's where our plus X minus X or plus concentration or minus concentration comes in. Remember, this is going to be plus some kind of coefficient X or minus coefficient. We have no zeros in our initials, so we don't know which side needs to increase. We have to then figure out which way it's going to shift equilibrium based on Q versus K, just like we did in the other problems. Okay, so to do that, then we're going to have to do a Q versus K. So to figure out our Q, we know Q is the same thing as a K, except that it's at non-equilibrium position. So a Q is still, if you recall, multiply my products and multiply my reactants. None of these are raised to a coefficient because all of them have ones in front. Okay, continuing on, we're going to figure out what Q is. Q in this case is going to be 3.33 times 10 to the negative first times 3.33 times 10 to the negative first divided by 3.33 times 10 to the negative first times 3.33 times 10 to the negative first. So when I multiply that, I get 1.00. Okay, so then we can do Q versus K. I'm just going to go do it up here. I'll keep it in order. Let me do it down here. Well, let's go back up and remember what our K was. Our K was 5.10. So then we're going to come down here, and remember we always want to think of OK or Q versus K. So this is 5.10 and this is 1.00. This is supposed to be versus. Okay, I got the Q from my calculation. I was given K, so I know that this is going to be my sign because 1 is less than 5.0. So that tells us which way Pac-Man's going to travel. It's going to travel to the right. So I think of Pac-Man then being right underneath here as the arrow. So here's my Pac-Man, right? Pac-Man's right here. Okay, I'm going to draw my little Pac-Man. So artistic, I know. You're jealous. Okay, Pac-Man can only eat positives. So in equilibrium, Pac-Man doesn't eat dots, he eats positives. So this is going to be plus x and plus x because he's going to travel that way. He can't go the other way. The way he's traveling is to the right, so that indicates that this side is going to be positives because in order for him to move forward, he has to eat positives. That by default makes this negative x and negative x. Remember that this would technically be a 1, this would be a 1, this would be a 1, and this would be a 1 because these coefficients all have 1 in front. So now we can figure out what our E is. So for this one, it's going to be 3.33 times 10 to the negative first minus x. For H2O, it's 3.33 times 10 to the minus 1 negative x. Over here for CO2, it's going to be 1.33 times 10 to the minus 1 plus x. And H2 will be 3.33 times 10 to the negative first plus x. I'm going to do this just to keep this stuff visually organized. Okay, so in order for us to, we have no way of solving for x this time because we don't know what x is equal to. We have no equilibrium value. So then we're going to go into K and we're going to plug in. Remember what our expression is. You can see it right here. It's the same as Q, except it's going to be K. So we're going to plug in. So then we're going to plug in the concentrations at equilibrium. So 3.33 times 10 to the negative 1 plus x, that's what this is, times 3.33 times 10 to the minus 1, pardon me, plus x on the bottom. I have to have CO and H2O, which are right here. So this is going to be 3.33 times 10 to the minus 1 minus x, and 3.33 times 10 to the minus 1 minus x. So these are going to be the same thing. You can think of as this, 3.33 times 10 to the minus 1 plus x squared. Let me give myself some more space. Over 3.33 times 10 to the minus 1 minus x squared. And remember, we already know K. We got that from the problem. So how do I solve for x? Well, if I have a squared over a squared, I can take the square root of both sides. So I'm going to take the square root of this side and the square root of this side. So 5.10 in my calculator, square rooted, or square root sign, is going to be 2.26 times 10 to the 0, so technically just 2.26. Looked at that too quick, or I wouldn't have done the times 10, equals 3.33 times 10 to the negative 1 plus x, and 3.33 times 10 to the minus 1 minus x. When I square root a squared, they go away. So our next step then is to solve for x. To continue solving for x, we're going to then cross multiply. So I'm going to put this over 1. I'm going to cross multiply. So this is going to be 2.26 times 3.33 minus, I keep saying minus, sorry, times 10 to the negative first minus x equals 1 times 3.33 times 10 to the minus 1 plus x. So I'm going to distribute this through. So 3.33 to the 1 negative times 2.26. So this is going to be, and I'm rounding to 3 sig figs every time here. So if you're not doing that on your calculator, you might get a slightly different answer. Times 10 to the negative 1. So that's that times that. And then I got to make it go through here. So this is minus 2.26x equals 3.33 times 10 to the minus 1 plus x. Now I'm going to combine like terms. That's equals. So I'm going to put X on this side. So I'm going to minus X from each side. And you don't have to show all this work necessarily, but the more work you show me, the more I can help you. So if I do just that part, I get 7.53 times 10 to the minus 1 minus 3.26x equals 3.33 times 10 to the minus 1. Okay, I'm still combining like terms. Now I got to get the non-x on the left-hand side to the right. So I'm going to subtract 7.53 times 10 to the minus 1 from both sides. Again, you don't have to show all this, but the more pieces you show me, the better I can help you. Okay, so then I'm going to get negative 3.26x equals, so I'm going to do 3.33 to the 1 negative minus 7.53 to the 1 negative. And I get on this side negative 4.20 times 10 to the negative first. Divide both sides then by negative 3.26 to solve for x. And I get x to be 1.29 times 10 to the negative first. That's just x. We're not done. I know, you just gasped, but get over it because we're not done. I want to make sure I can come back and read this later, so I'm going to make sure I know that's a 9. That's the value of x. So now we're going to go up here and we're going to plug that in to these spots to get these concentrations. Okay, so I'm going to do my best to squeeze that in here. I'm just going to change ink color so you can see a little clearer. So go back down. I'm going to figure out that is 1.29 to the negative 1. Okay, so we're going to take, and if you want, these are going to be the same, right? So you can kind of think of it like this. 3.33 times 10 to the negative 1 minus 1.29 times 10 to the negative 1. So 3.33 to the 1 negative minus 1.29 to the 1 negative. And I get on this side 2.04 times 10 to the negative 1. And then I get these two are going to be the same value because it's the same math. So this is going to be 3.33 times 10 to the negative 1 plus 1.29 times 10 to the negative 1. So 3.33 to the 1 negative plus 1.29 to the 1 negative. And this side I get 4.62 times 10 to the negative first. So then you can tell me the concentration for CO and the concentration for H2O would be 2.04 times 10 to the negative first. And then the concentration for CO2 and H2 would have been 4.62 times 10. Let me try to write that a little clearer. Sorry about that. 4.62 times 10 to the negative first. I just looked up here and realized that I had a slight mistake in what I wrote here. This should have been H2O. I'll go back in and edit the video, but you're going to see all this in here. That should have been H2O. I may have said it, I just didn't write it. I don't even know if I said it, but I'll check the video. But anyway, I have to put in here what was on the bottom. CO and H2O should be on the bottom. I just got sloppy. So I will go and edit the video. Hopefully that'll make a little more sense if you were confused. So I am done. I can report all my concentrations.